What track is this? Okay. It is the active queue management track. Actually, yes, this is the active queue management track. We're talking about load balancing, buffers, job management, et cetera, et cetera, et cetera. I'll be your track host for the day, and it gives me great pleasure to introduce the first speaker for the day, who's both charming, witty, and urbane, and thank you, Mahesh, appreciate it. And yeah, I'm the first speaker, so there you go. So, two people got it right at the start. That is useful. As the day goes on, for those of you who are going to hang out and listen to at least some of the other talks, what you're going to get is a bit more detail about techniques, mechanisms, modalities that you can use to do job management, queue management, essentially how you can and should be dealing with systems where you've got requests, producers and consumers, and you can't really control the rate at which stuff is coming in the door. What do I mean by that? The problem at hand is most of the stuff that we are building tends to consist of stuff that consumes data. And, or you're building stuff that produces data, which is fine too, but the thing is you rarely have control of the other end of the system. So if you're building stuff that consumes data, hey, you may not have control of stuff that produces the data, and when bad stuff happens, you know, what do you do? So that's kind of the overarching theme of what we're going to be talking about today. What was planning on talking about today was, amongst other things, two specific Erlang domain projects that actually implement a bunch of active queue management, job control, and so on and so forth. One of them was Ulf's job framework, which it turns out Ulf is giving a talk about it, so I'm not going to do that. The other one was Jesper's SV framework, which Jesper is giving a talk about that, so I'm not going to do that either. So instead, I'm going to tell you guys a story, which I hope you guys like. If you don't, please like it, or pretend. So the first talk, which is active queue management, is essentially the story of how I ruined my vacation. And essentially what, at a very big picture level, what this comes down to is not my vacation, which was ruined, but it's about how it doesn't matter how good you build your system, how well you build your system, how much care you take about whatever you're building, there's certain things that you just can't avoid. And the point behind that is there are these things called black swan events, which those of you who know anything about financial systems or so on and so forth are aware of black swans. These are things that the once-in-a-lifetime events that just kind of show up and screw up all of your best laid plans. So to begin with, let me kind of briefly describe my company, what we do. Or what my previous company used to do. I used to run a phone company, Joy. By the way, for those of you who are interested in starting a phone company, don't. But used to provide phone services for small businesses, which, to be really precise, came down to we provided hosted cloud communications for small businesses, which is kind of a very cool way of saying we took a really boring thing that used to be done by really large systems way back when. We put them in racks and we slammed them in clouds, and then you end up with, you know, cloud communications doing phone stuff and whatever. Doesn't particularly matter, really. It's just like buzzwords there. The important thing is the numbers. When we started this back in '99, we had about 0 phone calls per second. Okay, 1 phone call per second, maybe. By the time about 2008 or 2009 rolled around, we were running about 1,000 phone calls per second. Actually, I think it was about 3,000. If you look at the number of simultaneous phone calls per second, simultaneous phone calls that you're running at scale, it was actually went up by about 4 orders of magnitude. And if you look at the API requests, to kind of back up here, this is one of these new age phone companies where you could access stuff over the web. IM, Twitter, Facebook, all that kind of jazz. Our HTTP API requests went up by effectively infinity. It was just some crazy number. I mean, you don't even think about it. By the way, this is all in one huge infrastructure that we're basically replacing components in real time, which, when you look at our infrastructure, we basically were kind of your standard stuff. You've heard this. You know how this stuff works. The thing is, we had these huge clusters of, we hosted stuff on Amazon, we hosted stuff on Rackspace, we hosted stuff on Joyent, we had our own hosting centers, multiple clusters across multiple geographic regions and stuff. All very cool and extremely fancy. So that's kind of the background, just you kind of know what we used to do. So let's talk about my vacation. That's not the Taj Mahal, by the way. That is a thing called the Bibi Ka Maqbara, which is in this absolute hellhole of a city in the middle of India somewhere. But there's some spectacularly cool sightseeing around there. This was built by the grandson of the guy that built the Taj Mahal as some kind of memento to his grandfather, I guess. But he didn't have that much money. So that's not marble. That's actually kind of concrete. I mean, not concrete, random blocks. But it looks like the Taj Mahal, and it's kind of cool. That's where we were going. Or that's where I was supposed to be going, because that's actually a picture taken by somebody else, because I actually never managed to make it there. That's the key thing. So, what happened? We had, big racks of computers. There's a little tiny failure on one of the nodes. Just stuff goes down all the time. Something went down. So what do? Restart the node. It's easy. We write everything in Erlang. Life is good. All you got to do is just restart the node, and poof, the stuff comes right back up. So, I actually happened to be there. This was, by the way, exactly 1 hour before I got in the car to go to the airport with my wife, who really needed the vacation, as did I. Hit the button, boom, restart the node. I mean, we're talking like, and when I say went down, I mean everything went down. Pow. Worldwide outage. Not good, seriously. So, by the way, when I said it's my company, it was my company, but we had a CEO, which was not me, and we got a board that I report to technically, and at the end of the day, worldwide outages are bad things, even if it's your company. So, really bad things. So, what happened? That little tiny loosely coupled infrastructure thingy turned out to actually be a big, huge problem, which we never thought about that way. So let's take the problems one at a time, because this kind of illustrates what happens when you don't think about emergent properties, what happens when you don't think about large-scale issues that can occur in systems, or even when you do, but you don't expect these things to happen. One of those nodes went down. The people on that node who are on their phone calls, right? Calls got dropped because something bad happened. The calls got dropped, so they promptly start calling back. That's what you do, right? Your phone doesn't connect, you just call back. So all those calls rolled over to another node. And you can kind of see where that one's going, right? So the calls go over to the other node, and in the meantime, the person on the other side who got dropped is also calling back, because they're like, oh, hey, what happened? Neither can get each other, because now they're talking to each other, and both of their phones are busy, so they both go to voicemail. You leave a message. What happens to the message? That's got to go in, it's got to get transcoded, it's got to get, fun things have to happen, so CPU utilization starts going up on even more nodes, because we do transcoding on different nodes. So now, the node that the calls are rolling over to is spiking. The nodes that do the transcoding are spiking. And people keep calling. You leave the voicemail and you call back again, because that's what you do, because it's maybe an important call. Just about now, what happens is our back-end systems that go, that session seems to be timing out. It reloads the session from storage. So now it's hitting the disks. So the disks are starting to spike. So our storage units are starting to spike. And in the meantime, this is the modern age. Everybody's taking to Twitter and Facebook saying, dude, what's going on here? Fix this, fix this, fix this. Hey, do you know Eptela's down? Eptela's down. Oh my God, Eptela's down. And HTTP requests are going in. All the social media stuff is horrible because every single one of those we track, we log, we maintain. Boom, boom, boom. Cascading failures. Second node goes down. And now you get the picture, right? It's like the third node goes down, the fourth node goes down. The second node went down about 2 minutes. It took 2 minutes, which is kind of cool. After the first one went down, the rest of the nodes went down approximately 1 attosecond later. It was like, I may be exaggerating, maybe a nanosecond, but still, poof, gone. So, yeah, total system meltdown, completely. So then, the obvious thing is, well, dude, didn't you test under load? Well, yeah, you do test under load, but up to a certain point. You got to have some metric somewhere, right? What do you test against? When you build levees against floods, you don't check against 1,000-year floods. You could. So you build against this, you get a 10,000-year flood. What do? At some point, you got to stop. That's a black swan. That happens. To kind of roll back, we kind of saw this one coming. We knew this was going to happen. We didn't expect the 10,000-year flood. We didn't expect the black swan. But we kind of saw this one coming because we had seen this before. We had still, in a different situation, I won't go into it, but the point being, it doesn't matter how well you plan or carefully you plan, something bad is going to happen. You're going to end up with a scenario that you didn't expect. Can you plan for that? It's not whether you can recover immediately, it's are you fast enough to get back in shape? So the news for us was when everything went down, it took us about 3 hours to come back up. On the one hand, that was horrible. On the other hand, we did manage to come up, which I'll get back to in a bit. By the way, to take a step back on this one, in 2008, during the elections, there's this very famous, in the US, if you're in the phone business, incident where, there are all these issues with elections in the US. There's something that happened in Florida in 2000 stuff. So in 2008, what the Democrats did was they set up all these calling centers where they said, if there is any polling irregularity, please call this phone number. And they got this really reputable, spectacularly cool phone company to provide the phone services on the other side. Us, by the way, in case you didn't get the point. But we did that. Total meltdown back then. That one wasn't our fault. That one was because even though we had this spectacular capacity, we had prepared for bursts and overloads, and we were set. Turns out that all the phone calls from Ohio were going through this one single exchange somewhere in Cincinnati. That exchange went down. Right? Nothing we could do about that. We got blamed, but that was an issue. So anyhow, back then there was this big postmortem, and everybody said, okay, well, this is what should happen when exchanges go down, when centers go down, and how you should recover from failures. Sounds good. 2012, Romney's campaign had exactly the same thing when they had all their servers in the Boston Garden, and they didn't have enough capacity in the Boston Garden to deal with all their servers. You'd think they, of all people, would have paid attention to this. Capacity management, but you don't. Stuff happens. The bottom line being, stuff happens. Capacity management issues, overloads, things along these lines. And the question is, how do you possibly recover from these things? Or how do you actually plan for these things? Or actually, if you take a huge step back, how do you know what to look for in these situations? So let me kind of take these way back, and put it in a simpler context, back to where I started. At the end of the day, most of these problems are, you got a bunch of producers, you got a bunch of consumers. Producers are producing stuff, consumers are consuming stuff. If you got enough capacity to deal with all the producers, doesn't matter how much you produce, this talk's not for you. I mean, it's irrelevant. You're happy. And if it's the other side, if you're the producer and you know there are enough consumers to deal with whatever you're doing, you don't care about it either because you're happy. The question is, what happens when there's a mismatch? How do you deal with that mismatch? And to take this yet another huge step back, this talk is also about how, or what you're going to see over the rest of the day is how we don't learn from history. We never learn from history, and I wish, I think, in fact, I'm fairly certain that the quote, "we don't learn from history," has been restated originally about 1 million times. So, there we go. So, what do you do if you don't have enough time? The point is you just go, yeah, make it faster, make it faster. Well, can you make it faster? What if you got disks in the loop? Can you make those disks faster? Well, put SSDs in there. Well, can you do that? Is it still fast enough? Put RAM, use caches, do whatever. Oh, great, wonderful. Maybe there's a human in the loop somewhere. Seriously, order taking. To take a step back, a friend of mine went to Amsterdam to become the COO of this huge multi-level marketing company. And he showed up. It was this $2 billion a year company. He showed up. It turns out the entire back office was run off of Excel and Post-its. It was. And by the way, this is like, thousands of orders a day. But yeah, they had Post-its, they had Excels, and there's always a human in the loop. It turns out that is a good thing because that implicitly put a limit on how much stuff they could shove through the system. There's a human to the loop. The phone rings busy. That's it. There's nothing you can do about it. Works. Or not, depending on what you're trying to do. Right? Yeah, fine. Whoa. Hello. And this is actually a classic example. Your computer freezes. What do you do? Excuse me a moment. Woo, we're back. So, you put stuff in a queue, right? That's it. So instead of Post-its, you have somebody, instead of just have somebody taking calls and putting up something up on a Post-it, you have a receptionist, an admin, who takes the calls and says, "Please hold." And when the next person frees up, they pass the call along. Great, queuing. This, by the way, is the first thing that everybody re-implements. Put things in a queue. Problem will get solved. It's true. And somewhere I did something. Question is, what did I do? Maybe this. I shall just click on the little arrow and that shall solve my problem. So let's look at queues. Buffer bloat. Is buffer bloat an issue? Seriously, if you don't know what buffer bloat is, don't worry about it. It probably is going to be an issue for you. If you do know what it is, it probably could be an issue for you anyhow. Let's make this much simpler. Put everything in the queue. This is great. Take us as an example. System went down, just queue up the requests. And once the system comes back up, you can start processing it, right? What if you can't draw down the queue fast enough? You now have people blasting it on the back end, and you can't pull things off the front end back end up. Eventually, your queue explodes. It happens. I mean, that's just going to happen. Back pressure? It's possible. Back pressure. I think you're going to be talking about back pressure later today. Steve Vinosky will be giving a talk which includes back pressure, amongst other things. So, to kind of cut to the chase, yeah, put a queue in there. You got possible problems. If none of these apply to you, oh, happy days. This is gorgeous. If any of these apply to you, you got a problem. You may not have a problem today, but if, God forbid, actually not God forbid, hopefully, whatever you're doing works, and the project gets accepted, and or it actually sees the light of day. Remember, something like 90% of every single project everywhere never makes it to the light of day. But if you happen to be one of those 10%, you got a problem. There are possible solutions to a lot of these things. They're not perfect solutions, but they're possible solutions. The easy, simple one, is it programmable? In the world of SIP, in phone calls, some HTTP stuff too, you can actually tell people programmatically, hey, retry this request after 30 seconds. That buys you valuable time while you bring your system back up again. Yep. Useful. That's, in many ways, one of the best approaches, if you have the luxury of being able to do that. Sometimes you don't even do that. You use behavioral techniques. Put that thing up. You know, on the net, most of the time, nothing's actually happening back there. And yet you stare at the screen like, oh, hey, yeah, something's going to happen. And after about 30 or 45 seconds, you click reload. Hey, the person at the other end bought 30 or 45 seconds. It's awesome. Behavioral psychology, it's valuable. Remember this. There's self-managed techniques that you can use. Airports use this all the time. You just put up, you let people figure it out. You make the clients intelligent. Even if they don't know that they're being intelligent, you make the clients intelligent. Which queue do I go to? You look at the lines, you pick the queue that's shortest. Works. If the cashier vanishes from one of the queues, from one of the lines, everybody just leaves and goes over to the other ones. You didn't have to do anything. The supermarket didn't have to do anything. People manage themselves into the other queues. It works. In fact, do you know one of the best practitioners, this is going to sound kind of weird, but one of the best practitioners of queue management, active queue management to be precise, the airlines. Seriously, who knew? Turns out they've been doing this for 50 years or more, ever since it started taking off. They know how to deal with this stuff. The point about airlines is, this is what you always end up seeing, right? Cancel, cancel, cancel. Oh, suck. Why can't the planes just deal with this stuff? Why can't the airlines just get me to my destination happily? Actually, it turns out they are for the vast majority of people. There's some small set, very vocal set, sometimes you, who's unhappy, but yes, they're good at this. But the point, the underlying point behind active queue management, to bring this full circle yet again, is what do you do when you do not have control? When, to put it mildly, something's got to give. You got more producers than consumers can deal with. You got less consumers than the producer wants. You got to drop something. You got to do something which involves not making everybody happy. Somebody's going to be unhappy. The question is, who do you pick to be unhappy? And this is the million-dollar question. This is the difference between a successful business and an unsuccessful business. This is the difference between a successful application and one that, dies badly. So one of the things that I tend to see a lot of is this stuff, how you do active queue management, it has been reinvented so many times, it's not even funny. And by the way I realize that the airlines do this is a friend of mine actually came to me and said, oh, you're always ranting about AQM. We've been doing this for 50 years. Like, wow, okay, so I did something I could learn too. So let's take the simple case. You got stuff coming in the queue on the left side, somebody reading it off the right side. What do you do when there's not enough, the queue can't grow infinitely, and there are not enough people to read stuff off the right side? The simplest, the most obvious one, the one that everybody always does right off the bat, it's called tail drop. Just start dropping stuff when the queue fills up. It's easy, it's simple. It's also really, really, really not a good solution. Because it's not even worth getting into, but basically what it boils down to is your entire system can slow to a crawl. Good way to think about this, think about planes. You got, let's say, think about the US. You got planes that got to go from New York to San Francisco. It's a 6-hour flight. Let's say there's just not enough air traffic capacity to deal with people going over. If you just don't even let the plane take off on this end till capacity frees up in San Francisco over at that end, you now have an immediate 6-hour delay on every single flight. Because you got to wait for this plane to get all the way over there and say, oh, hey, yeah, I'm here. Then you let the next one off. 6 hours. That's bad. That's not going to work. Tail drop, bad idea. But, people do it anyhow. So years and years ago, way back when, Van Jacobson. Anybody here not know who Van Jacobson is? Hands. 1, 2, 3, okay, 4. Okay, see, there now we're starting to get this. There are people that don't know who Van Jacobson is. He's God. He may not be the God, but he's certainly a God. Rescued TCP/IP back in the mid-'80s with something called Slow Start. Probably he's forgotten more about networking than we'll ever know in our lives, and so on. Between him and Kathy Nichols and a couple others, I mean, they're like the genii in the world of TCP/IP. So anyhow, this guy, way back when, came up with something called RED, which has a bunch of different, it doesn't particularly matter what it stands for. It's random early detect or random early drop. But the whole point is, it is a mechanism by which you can actually figure out what to do with your queues when they start filling up. So here's a simple way to think about this. Instead of just doing tail drop, which is what you usually do when your queue fills up, get slightly more intelligent about it. What you do is, you look at your queue and you say, as my queue starts filling up, the closer it gets to getting filled up, the more requests I drop. Let me repeat that. You start dropping requests even before the queue fills up. Sounds like a bad idea, but it's actually a really good idea, because what it's doing is it's telling people at the other end, oh, hey, there might be some issues. I may not be fast enough to deal with this. Maybe you might want to slow down your transmission a bit. This is a curve that basically says these are different rates at which you can drop stuff. Early on, don't do anything, but the closer you get to full, so till you're about 70% full, don't do anything, just take stuff. Between 70 and 80, drop 10% of your requests. Between 80 and 90, drop 50% of your requests. It's an idea. It works. It actually works really well. It's bloody hard to tune, but it works remarkably well. They actually, airlines do this all the time. Classic example is in New York, you got 3 airports, LaGuardia, JFK, and Newark. Newark always gets a shaft. Basically, whenever there's any problem with the airspace in New York, they start telling Newark, you are going to have delays. Even before it gets there. That's why, it's a well-known thing. You never fly into or out of Newark between 11 a.m. and 4 p.m. Just don't. By the way, if you ever think about it, don't. So there's about 80 bajillion different ways in which you can do these things. There's something called FRED, which stands for Flow Random Early Detect. These are actual terms, by the way, terms of art. What FRED basically does is it says, instead of just dropping things from the queue, look at the actual traffic going through the queue and say, which producer is sending to which consumer. Because what you might have is you might have one person at this end sending a bajillion requests, and everybody else is just kind of occasionally talking. So just shut that one major request down, or start slowing them down, and the rest kind of deal with it. The thing is, you got to put more intelligence there, you got to track things a lot better. It's harder, but it's good. There's another thing called preferential drop, which basically translates to, when you're talking about intercontinental travel, you basically say, you know what, if you're flying from London to New York, that's kind of a big deal. You can't just turn back when you're halfway over the Atlantic. So those get high priority. Any traffic within a given country, those get the shaft. So the equivalent from our queue side, just to kind of like flog this dead horse, is you basically go, okay, between two Erlang nodes, a heartbeat between the two nodes would be a very good thing to not drop ever. Yeah, that's an inside joke for a lot of you, so there. But yeah, that would be an example of a preferential, being good about that. There's something else called, weighted read. This is now where life gets even scarier, which is you start doing not just transatlantic stuff, but you go, you know what? The London to New York one is really, really important because that's where our masters of our universe, the financial people, that's the route they take. So don't drop any of those. But anybody coming from Frankfurt, screw them. They're not important. That's an inside joke for some other people, so we'll leave it at that. So there's a million more. Stabilized read, robust read, adaptive read. There's also something called Blue, which is, it's supposedly a joke. I don't know what it is. There's something called Choke, which is choose and kill, which is something that Microsoft helped out with, which about 0 people use. But it's there. That's not an anti-Microsoft statement, by the way. It is like, even for complicated stuff, this was crazy complicated. And, pass it. So way, way, way back when, and I mean way back when, because Red was complicated, Van Jacobson kind of stepped back and said, hey, I figured out a solution to these problems. I'm just going to make it. He modified the Red algorithms and the Red methodology to essentially make it into a feedback loop. Effectively, what he said was, allow the queues to automatically sense what their current status is and figure out what to drop based upon how full they are. It is a paper that he submitted. This is in the late 80s or early 90s, 1992, I think. And by the way, I'm not making this part up. He submitted the paper. One of the examples that he had in the paper was a toilet. If you think about the way a toilet is structured, it's like even if there's a leak, the tank still kind of fills up. You've seen this. There's a leak in the toilet in your house, it fills up. It works, it never overflows. There's all this fun stuff that happens in there. He had that picture in there. It got rejected by the journal because there's a picture of a toilet in the thing. I'm seriously not making this up. Some people have no sense of humor. But so Van Jacobson being Van Jacobson, basically being an angry god at this point, basically said, screw you, I'm just not going to publish this. Never saw the light of day, which probably changed the internet world for the worse for quite a while. But that's, however, he did do something. He created something called Codel, which control delete or a couple other things. Jesper is going to talk about this afternoon. Codel essentially is a completely different way of looking at queues, where he basically said what's important about a queue, and this is one of those ridiculously obvious things in retrospect. He said what's really important about a queue is not how many things are going through the queue and whether you have enough producers or consumers or what the endpoints are. What's really, really important is how long each item takes in the queue. That's the only thing that matters. I know, you're kind of sitting there going, well, duh, what's your point? It turns out that was a, wow, we never thought of that kind of moment for a lot of people. It also means the number of things you need to measure in the queue are ridiculously small. You just measure the time that something takes to go through the queue. And it kind of automatically fixes a bunch of other stuff. The algorithm's actually very simple to implement. Jesper, in his safety valve package, which, like I said, he's going to talk about this afternoon, actually has a working version of Codel in this thing. So about Codel, one of the things that I've noticed is when people go about re-implementing queue management or active queue management in whatever systems they're building out there, everybody reinvents Codel. Everybody. And they all get it wrong. Seriously, go check out the paper, read it. When you read the paper, if you're doing anything with queue management, just read the paper. You're going to read the paper, you're going to go, I should have thought of that. It's a couple of little tiny things, but they're important. And this, to take one huge step to the side, but not step in the way of something. Pretend I took a huge step to the side. The problem with accident? No, water. The problem with active queue management is emergent properties. Things happen in systems which have busy queues and so on that you can't. It's actually quite possibly an NP-complete problem. It is not predictable. You don't know how the system's going to react when it gets close to the edges. It is a chaotic system, effectively. These are things that they're abstruse, they're obscure. You may think you know what you're doing, you don't. By the way, that's not because you are not smart, it's because nobody does. It is that's why it's called an emergent property. It just, things happen. So, for those of you who are not aware of what slow start is, in TCP/IP, way back when in the mid-80s, the internet almost shut down because there were problems in the way TCP/IP was structured back then. It is not something that you could reason from first principles. It is something that happened just because of the way TCP/IP's windows are structured. There's this thing called retransmit window and so on and so forth and whatever. Just trust me, it is bad. And effectively what ended up happening was, I had seen this too. I had no idea why it was happening. That's because I was in Van Jacobson. But the point is, I was sitting in a room, there was my computer, there was a computer right next to me. I couldn't interact with the computer right here, even though they're plugged into the same router. But I was perfectly happily interacting with one in Chicago. I was about 400 miles away. So going 400 miles was easy, but going right next to me was not possible. Which wasn't because of a crappy switch or something, it's because TCP/IP was busted at the time. It was like a problem. And Van Jacobson eventually figured out that it is something called slow start, which he came up with a patch for. For a while, it was called Van Jacobson TCP/IP, and then it became TCP/IP. So nobody even remembers that there was a pre-Van Jacobson TCP/IP, because that's just the world that we live in nowadays. It's like you don't realize you're breathing. You're breathing. It just is. So anyhow, which is a long way of getting back to Codel. Go read the paper. Take a look at it. You'll see a couple of edge cases. At least one of those edge cases is something that you will say to yourself, aha, I wish I had thought of that. And then you'll quite probably go about saying, yeah, I did think of that one. It's in the code. But that's okay. Just do it. Everybody will be happier. So, testing. Duh. Testing. You do this, you put in active queue management, you read the paper, you do Codel, test it. It's going to work. Maybe. Maybe not. Because quite frankly, remember the bit about black swans? They're going to happen. They are going to happen. Whatever you do, wherever you go, whatever you implement, something bad is going to happen. This is, some philosopher probably said it a lot better than me, but I believe, technically speaking, the term is shit happens. It's going to happen. So when you kind of step back, what you need to do is ask yourself a couple of things. One, do I need to worry about queue management? Yes or no? The answer is no. You're probably wrong, but let's just pretend the answer is no. Okay, fine, great. That's good, that's good. I mean, it's a good business. If you do need to worry about queue management, look at the things you control. Make sure that the things that you control are under control. That's a huge chunk of everything that we've been talking about, the origin story behind Erlang, fault tolerance, reliability, blah, blah, blah. That's all about making sure that the things you control are actually under control. Great, do that, happy. You wrote the perfect application, and the things that you control will never, ever crash. Happy days. So that's two things you got going for you right now. The third one is, where all the magic needs to happen. What about the things you don't control? Hey, my app suddenly became massively popular. Ouch. Huge downloads, huge server hits. Oh, people are actually using my service. Wow, problem. Good problem, but problem. You should know. Spill Games, Exhibit A. Wow, we're successful. Meta issue with Spill Games and queue management. Development talent, where do they get people from? That's also a queue, right? I mean, you don't have enough people to solve the problems you need to solve. That's a problem you got out there. There's queue management everywhere, you just never think about it. So think about the things you control, make sure it works. Look at the things you don't control. Try and figure out what your business requirements are associated with the things you don't control. And that is going to determine the things, the people you can make unhappy. Back to airlines. I travel a lot on business. I get treated extremely well by the airlines. Because I give them a lot of money, business money, last-minute ticket money. So if there's a problem, before the airline even tells anybody there's a problem, I get a phone call saying, oh, hey, yeah. If I don't buy one of those tickets, let's say I'm just going somewhere on vacation, I travel once a year. I am like the last person. I'm the first person that they go away, we don't care about you. Right? I mean, this is the way the world works. This is what the airlines determined was business travelers, important. Non-business travelers, don't give a shit. I'm not saying you shouldn't care. What I'm saying is figure out who or what or where or when you can make things or people unhappy. Make those unhappy. Because it's a lot better than making the important people unhappy. Seriously. So basically, whatever your business is going to determine what your strategy is. There is no universal strategy. Do go read the paper. And at the end of the day, agility is your friend. Being able to recover and react rapidly is basically what's going to be the difference between being successful and not. And with that, I shall come to an end. Any questions? Yes?
Is the paper, you mean the one in Q?
Yes. Yeah, exactly. That's it. Yeah, done. I know. So Piers read it. Piers is a smart guy. Yeah, exactly.
Can you go back to the random drop theme?
Yes.
Did I get it right that the curve has to be the other way around?
Not necessarily. The whole point is you don't know. It depends upon your business requirements, your situations. You can postulate a good catch, but the point behind that is every specific business or every specific problem has a specific implementation relevant to it. So you could, as an exercise to the reader, which I always hate, you can come up with a scenario in which that's exactly what you want. You can come up with a scenario where you don't want any of them. There are also scenarios where you can say stuff like, everything goes through till it's 100%, at which point I do tail drop. Fine, whatever, but you do it. But yes, exactly. Excellent. Thank you.